Yes. So we will start our discussion where we will first discuss our questions related to uh, the assignment number 8. In that, let me start. So the first question is, which of the following statements are true? Again, it's A and C. The leading lag switches achieve ZVS for light load condition as well, because it's the output inductor which comes in series with the L leakage, and that has good amount of energy to discharge the C1 and C2 capacitance of or discharge or charge C1 and C2 capacitance of the switch S1 and S2 such that they change its states, and that's when the diode across the diode or the body diode connected across the switch will get turned on, and that's when switch will achieve the ZVS. However, in C, the increase the value of resonant inductor helps in improve possibility of lagging lag. Yes, because during the during the turning on of the lagging switch, it's the L leakage which will come into picture, and that's when we have to ensure that the L leakage is sufficiently large enough such that even at light load condition also it has so much of energy that it can change the states of C3 and C4 capacitor such that the switch which is going to turn on will have the diode first gets turned on, the diode for body diode for that particular switch will get turned on, and that's when we'll achieve the soft switching of the switch. Then your this is there. Then so these are the two conditions where our this full phase shifted full bridge converter, the things related to that. In question number 2, if we see for question number 2, so for question number 2, it is a straightforward where we just have to do the we know that our V naught and V in expression, since it is a Buck derived topology, it is nothing but V naught is equals to N V in D, N V in duty ratio, where N it is given 1:1 transformer, so N equal to 1 is been given. V naught by V in is given as 0.4, that implies your duty ratio is 0.6, and we know that our delta by 180 degree is nothing but 1 by D. So we know our 1 minus D becomes 0.4, and this multiplied by 180 will give you directly 72 degree angle. So that is a quite a straightforward question. Similarly, if you see the question number 10 also will have the same kind of thing. It is the same kind of thing. It uses the same kind of for this structure where delta is given as 90 degree. So that means our 1 minus D will become 90 by 180, which is become D equal to 0.5, and that's when our V naught becomes 100. Yes, there is a mistake in the range given. We will an answer given. We will change the range to 90 to 110. So that's where if you put the correct answer, it will be corrected. So that's the question number 10 for you. Then comes the question number 3. In question number 3, when we solve this particular thing, question number 3, let me see the question number 3. Again, question number 3 is for it is asking for the minimum time period for which the leading switches achieves the 0 voltage turn on. That means we need to ensure that the capacitor C1 and C2 discharge, or when the capacitor C1 and C2 changes its state in such a manner that the switch which is gonna turn on, the body diode for that particular switch will turn on first, and that's when you will receive the ZVS. Again, in the question it is given that assume that the necessary condition, which is the energy of the inductor, which energy which is there in the current which is going through the inductor connected at the pole of the half bridge, must be very much greater than the half CV square, half C1 V in square plus half C2 V in square. So that condition is met. That assumption is, that question it is already given. Now we have to find out the required dead time to put such that the current which will fall down because of the DVDT which is happening due to the current which is coming out of the half bridge. So for that, simply we can write V equal I equal to C dV/dt. I is the constant current which is actually the reflected output current. So it's the I1, and since there are two capacitors, one capacitor is charging, another capacitor is discharging. So you have to take C1 plus C2. Here C1 and C2 is equal to, we have taken 2C, and the voltage is, the amount of voltage which gets changed is nothing but V in. So our dead time is nothing but 2C V in by I1. That, we have already discussed in the lecture as well. And that when we put it these equations, and when we will, and then we will put that thing here, we will get nothing but 16 nanosecond, and you have to give answer in just a nanosecond. So to just write the 16. So that's the minimum dead time. So that's the minimum dead time which you have to provide. And the dead time, if you don't put the dead time equal to this, then you will not achieve the zero voltage. The voltage across the switch will not come down to zero. It may be less than V in, but it is not equal to zero. So that means you will, that particular condition is called as the quasi short switching case, or quasi ZVS condition, or it's sometimes also called as a valley switching. But here we are getting the we wanted that the zero voltage turn on should be there. So we want the voltage should drop down completely from V in to zero from one of the capacitor, and in other capacitor it goes from 0 to V in, and that's why we got this particular relationship. Then comes your then comes your question number 4. In question number 4, it is given that the phase shifted converter, this values is being given. Now here in this question, what we have to find out, we have to find the minimum dead time we have to provide with the for the lagging leg. So here we discuss the leading leg, where it is quite a straightforward, but here since the secondary got short circuited, so the L leakage will come in resonance with C3 and C4. So that's why we have to see, there will be the sinusoidal variation of currents which will be happening. So we have to ensure that the voltage across C3 and C4 changes is steered in such a manner that they reach to the zero voltage. So for that, the formula what we have derived, we have already derived in the class. It's straightforward. 1 by omega 1 sine inverse V in by V2 under root 2C by L leakage, where W1 is nothing but 1 by under root 2 L leakage C, where we assume that C3 equal to C4 equal to C. So that we got the omega 1 to be nothing but 10 raised to power 7 radian per second, and that's when the dead time required is nothing but minimum dead time required, because we want the dead time should be greater than that, because that will ensure that voltage reaches to its 0 point. So that's when we can write 1 by 10 power 7 sine inverse V in by I2 under root 2C L leakage. C we know, L leakage we know, which is 10 microhenry given. However, the output voltage is given as 50 volt and output load is given as 10 ohm. So our output current, average current is nothing but 5 ampere. And since we have already given that we have the ripple is very minimal, so we can assume that the current is nearly constant, and that amount of current will actually get reflected onto the primary side, since we have transformer ratio 1:1. So directly 5 ampere will jump on the primary side, and that when you put it in this formula, what we will get is nothing but 20.13 nanosecond. Yes, the values given was slightly wrong. We will change this value as well in question number 4. This particular answer and this range we will change. Then comes the question number 5. In question number 5, it is in question number 5, when we see, we know our formula D loss is equal to 4 L leakage N I naught F switching by V in. And in this question, if you see, our V in voltage is given as it is going from 200 volt to 465 volt. That's a variation you have. And it is given that the maximum duty loss which is allowed is 10%. So that means the maximum duty loss which it can go is 10%, that means maximum duty which you can get, effective duty which you can get is nothing but 0.9 times. That means you can go up maximum up to 0.9. So we can write V naught is equals to VR min Dmax value. That means this is the maximum duty ratio. For that duty ratio, to keeping the same output voltage, we have to reduce the VR min. So we have to take the minimum. We have for minimum we are also, for minimum rectified voltage also, at the maximum duty ratio we should be in a position to achieve the same amount of V naught voltage. So for that, V naught is given 90 volt, constant 90 volt given. Dmax it can go is 0.9, which gives the minimum value of VR which it can go is 100 volt. And since my input is varying between 200 to 100, so we must ensure that for the 200 volt also I should be in a position to generate the 100 volt, and for that we get the turns ratio to be 0.9, and that turns ratio when you put in this particular formula, we will get the thing nothing but equal to 10 microhenry. So that particular thing we should keep such that our value, we will able to achieve the required operation of the circuit. And our FCT is given 100 kilohertz. Our I naught is already given as 10 ampere, and 0.5 we have calculated. For this one, V we have to keep it for the minimum value, because the duty ratio, the N and all we have calculated for minimum value, so we can keep it for the minimum value, and then we can calculate the L leakage. So this is how you can obtain this particular what you can say, this particular answer for this particular question, question 5. Now let me go and see the next question. In question number 6, which of the following statement are true? Here it is given that it is having a constant output voltage. So with increase in input voltage, our effective duty ratio decreases. So answer B is correct. So A is wrong, B is correct. So we will correct this particular option B. That means with increase in the input voltage, the effective ratio decreases. And in the C and D part, since our resistance value is increasing, that means our load current reduces. Since our load current reduces, we know that our D loss is directly proportional to the load current. So our D loss value increases. The moment our D loss value increases, our effective duty ratio decreases. So that is what we have, you have to achieve this one. So so the moment the load resistance increases, I naught reduces. I naught reduces means your D loss reduces. D loss reduces means the D effective increases. Since the D effective increases, so your C value is the correct option out of C and D. So it's a C and B which is correct. B and C which is correct. We will update it accordingly, the options. Then question 7, yes, question 7, there was typo mistake from our side. It has to be leading leg, but it was lagging leg. So we will consider that, and A, C, D, all three options are correct in A, C and D. All the three options are correct in this particular question. So we will put that all the three options correct, and then re-evaluate that. Then question number 8. In question number 8, again it's quite a I have already discussed in the last class. We have to calculate the resonant frequency when the lagging switch is turning off. That means omega 1 is equals to 1 by under root 2 L leakage C. L leakage we have to take, which is 10 microhenry, not the other inductance, only the L leakage inductance. And from there, when we put this value, we get omega 1 equal to this one, and that's when the resonant frequency in kilohertz we will get divided by 2 pi, and that we will get to be value as 112.597 kilohertz. So we have given the range. If it is in this range, the answer will be correct. In question number 9, which of the following statement is true? We have already discussed in the class that with the change in the input voltage, there will be a term correspond to that change in the input voltage, which is a dV tilde, and this dV tilde is actually having the same kind of effect as that of the input voltage effect, because if the input voltage reduces, d tilde reduces, that's when your you know it means that's when your this dV term will get added up in the duty ratio, because your duty ratio also effective, I mean the effect on the effective duty ratio will also increases. And for the current, it has the opposite it has opposite sign. As the inductor current increases, your d loss kind of term reduces, that's when your effective duty ratio is increasing. So what you can say is that it has the opposite impact. So that's why answer B and C is correct in this particular question. And then question number 10 we have already discussed. So in this assignment, question number 10, question number 7, question number 10 range will be changed. It is 100, so we will we will change the range. Question number 10. In question number 4, we will change the range. 20.13 is the answer. So those are the two changes in the numerical problems. And the option problem, it is this question number 6, which is B and C. In option 7, which is B and C. In question number 8, it is A, C, and D. The 3 options which will be correct. So that will be the changes which we will do, and again reevaluate the thing. And the for assignment number 3 and assignment number 5, I think reevaluation has been completed. So that you can check it. Then let me see some of the doubts. In the doubt section, the first question which was asked was, in this question, let's take the lagging lag case, where because of the current direction, see the current has to find a pathway. There is no channel which is formed, there is no diode which is in conduction, because of the virtue of the current direction, the current, I mean this particular portion is actually C3 is already charged, so D3 is already reverse bias, while in the bottom switch the C4 is not charged up, it is 0 voltage, but the current direction is such that it cannot flow from the diode D4. So only option which the current has is to find a pathway through C4 and C3 capacitance. Why? Because this C4 and C3 will come in parallel to each other, because when you are taking this current source, we will assume that this voltage source is not at all existing. It is like the superposition theorem we will apply, and we will make this voltage source short circuited. So that's why the current has two parallel paths. One is going through the C4, another one is going through the C3. So that is why the current direction is drawn in this manner. Then in this question, the question asked was, I think, let me see if Milind is here. No, he is not here. Let me discuss that. So his question was, when the secondary is short circuited, the L leakage will start resonating. In this particular case, S2 is on. So leading lag, one switch is conducting. On the lagging side, what happens is that again the same scenario, because of the current in this direction, it cannot flow through the diode D4 because of the direction. It cannot flow through the diode D3 because C3 is already charged to the voltage, some finite non-zero voltage. So diode D3 is already reverse biased. So current has to find a pathway, that's why it is going through the C3 and C4 capacitor. Now in this particular case, what happens, because of the secondary winding which is short circuited, the primary winding voltage is 0, so the circuit will be L leakage, short circuited, primary winding, and then you have C3 comes in parallel to the C4 resistors, and that will go around and it will come via S2 switch, come back to the L leakage. One part of the current goes to C3, wean, S2 switch and come back to inductor, Other part come back to the inductor current, other part goes to the C4 and then through the S2 switch comes over here. So that is why both the C3 and C4 will come into picture. The what you can say, the parallel combination of that will come into the resonance with the inductor L leakage. Now the question is, the C4, since it is closer to the winding, so the resonance will take place with C4. See the idea, see here we are drawing the switches in this direction, but that does not mean that in actual circuit it is laid down like this. It could be possible that this lagging leg is placed before the leading leg. Here for understanding purpose, for drawing purpose, we are drawn in this way. It could be possible that I put this point over here and I put this point over here, this B point over here, A point over here. So during that time you can say that your the other switch loop may be smaller as compared to C4 switch. So it is all depending upon the placement. However, whether it will be placed, I mean nearby or slightly far away, but what I am trying to say is that this current is enormously larger amount of current because it is reflected from the output side. Now since this current is larger amount there and kind of a constant current because of the current through the output current in the inductor. So because of that, what you will see that the effect of the bigger loop or smaller loop will not be that much as compared to when it would have been just the voltage source. So because voltage source is then only the impedance impact will come into picture. Here you are forcing the current through a kind of a, you can say, constant current source. So there the effect of the voltage drop and those things will not be too much prominent, because since here we are only talking about current through the inductor, which kind of making the current kind of constant. It tries to find a path in the circuit where it can flow, and that's when it makes the current constant, or does not resist the change in the current through the inductor. So that's the answer to that. Then there was another question, how did we write that change in current is equals to change in time? Okay, see what I'm trying to say in this particular part is, whenever there is the change in the current, there will be change in the delta, there will be change in the what you can say, the time period which is between going between T2 to T5, which corresponds to the duty loss. Now that time is there, so we have to find out only for that change how it will reflect in terms of the duty ratio. So what we are doing is we have to find the duty ratio corresponds to that. So that means corresponds to that change in the time period. So for that we have given it to be di del tilde di term, and that's why we have to find out that duty ratio, so that we have to divide it by Ts by 2, because all our duties which we define is the time period for which your VR voltage is non-zero, or you can say the rectified voltage is non-zero over the Ts by 2 period. So that is why we have taken Ts by 2, and that is why we will get this kind of expression. Question 4, I think this I have already answered. Question 6, this also I have already answered. Question 7, this also I have already answered. Question 9 also mostly it is answered. Yeah, question 8 also I have answered. Apart from this, any further doubts you have, please ask. Any other doubts if you have? If there are no doubts, yeah.
Good morning, sir. This is sir. I have a doubt. Like in some of the modes where C1 and C2 are on, while writing the current equation, we consider while that means we apply substitution theorem and we say that we are short circuiting the DC voltage source, and then we are writing the current equation considering the two capacitors to be parallel and then in series with the inductor. But when we are writing the voltage equation for the same thing, for the same circuit, then we are considering that voltage source. So, like, I'm having some doubt here, like, why is it happening like this?
Where in that resonant equation
Sir,
case?
like, Yeah, we can say in resonant equations also, like in lecture number 37. If we open lecture number 37 and you have drawn one of the circuit there where you have drawn the equivalent circuit, and you are like lecture 37 slide 10.
Okay. See here,
Yes,
here why it
uh,
is coming, because your this voltage whatever is there is already at V in voltage. The initial voltage of VC3 was V in.
okay.
So when you solve from that, you will get this. That is what I have written. No, from here. From here, I have written
Uh,
that only. You see.
like here we are writing VC3 is equal to V in minus VC40.
Why we are writing VC for VC40? Why we are writing? See, VC40 is this VC40. You are you don't have any doubt, correct?
No,
VC40.
sir, that
Ah,
I understood.
Now VC3. You see, VC3 is discharging. Can you see VC3 is discharging?
Yes, sir.
So it was at V in voltage. It was at
Hmm.
V in voltage. So that's why V in minus VC4, because with the same amount VC4 is going in the reverse direction.
But sir, if we consider this circuit which you have drawn here, then to if we see here VC3 and VC4 are in parallel, then to VC3
No,
and
so
VC4
that's
would
why.
be
See,
equal.
again, no. It is not like that. You don't understand. See, I agree what you are saying. Okay, sir. If it is parallel, then voltages are same. No, we cannot say like this. See, when the two capacitors are they are holding the voltages. Okay, and it is the time when you suddenly connected them in parallel. One is discharged, one is charged. So what will happen? They will rearrange their charges among them. Correct?
Hmm.
That will only happen. So that is what, during that instant, that point is happening.
But sir,
See,
again, I'm
I
not so
ask you,
sorry.
I ask you one. Suppose that one capacitor is there. It is charged at some V voltage. You have
Yes,
another
sir.
capacitor which is charged at zero voltage. Now you connect them in parallel. What will happen?
The second will start charging with.
Charging. Correct. That is what is happening. And first will start discharging.
Okay.
That process is what I am trying to say in this loop.
Okay. So like here will miss like, but can we say here that caviar won't be certified and VC3 and VC4 won't be equal means in parallel?
No, now see, during the initial period it will not settle, but over the, because there's a transient period, it will slowly settle down.
Okay.
It will slowly settle down to what it has to satisfy KVL, so it will slowly settle down. It is only because they are the
Uh-huh.
storage devices. They are not the just the passives which we have, which are there.
Okay, okay, sir. So, like we can say that for transient period, means KVL won't be satisfied for transient period.
Uh, um, you
I was confused between the voltage of
see,
VC3 and VC4.
and okay. If you wanted to do this one, okay, you do the KVL in this loop. What you will get? Let's say if you wanted to do KVL, you go
Now
from this point. VC3 is there, V in is there, so you will get the VC4 is equals to VC3 is equals to V in minus VC4 in this loop.
VC4, yeah.
You can do in that way also. That will be
That's what I'm saying, sir. That if we are trying to do the KVL thing, and
yeah,
if we are
yeah. You can do
assuming the
that.
V in,
Okay.
then it is satisfying. But
Yeah.
for
You can
writing
say, you can
current
take that.
equation,
Yeah, you take that. You take that. You can take that as well.
but again, if we are trying to write the current equation, then we have to consider the circuit which you have drawn.
Yeah.
So, so like for writing the KVL equation, we have to consider different
Okay.
circuit.
Yeah. You are correct. That is here you have to consider the KVL. Correct. No issue.
So, is it means
It is correct. Yeah,
my
correct.
thought is correct? Like,
Correct. Your thought is correct. Your thought is correct.
okay, sir. And sir, the other doubt was in some of the cases, I am confused between the voltage of VAB and the voltage across L leakage and the voltage across the VP.
Which one?
So,
Which one?
sir, like in this slide,
Hmm.
like wait, I will just find that slide. Um, in slide 7 in of this lecture only.
Hmm.
Sir, here we can say that VAB is 0.
Okay.
If VAB is 0, then we are automatically considering that since IP is constant, the voltage across the leakage will also be, the VL leakage will also be 0.
No, it is
So
not zero. It is not zero. Why? Because you have the secondary winding. From there, this part will come into get reflected over here. No, whatever the voltage which you get across this winding, that will get reflected over here.
across the primary winding of the
This
transformer.
VP across at that VP. So this side is short circuited. I agree. But you have leakage, and this voltage is now the active voltage, which is kind of reflected whatever voltage we are getting on the NS top NS winding.
Sir, sometimes I get confused. Like sometimes we are saying that means in this mode also we are saying that IP is having very less ripple, and therefore we will
Ah,
consider VL
okay.
leakage to be
Yes,
0.
yes. See, why I have taken IP equal to 0? The ripple on IP is nearly 0. Why? Because see, your that is the current which is a reflected current in the output inductor. That current
Yes,
is there, and output inductor current is generally kept very large, such that the ripple is nearly less than 10%. So less than 10% means, if you, let's say if your load current is 10 ampere, you are assuming the ripple to be peak to peak to be 1 ampere. So it is kind of, you can say, you can neglect that as well. You got my
okay.
point?
So, sir, like in some of the cases when we are saying, okay, VAB is some non-zero voltage, and then that voltage is taken at primary of the transformer, we say that okay, VP is equal to VAB, and that is reflected on the secondary side.
Where I
In
have written VP is equals to VAB.
means like when we means no, I'm not saying like this, sir. I'm saying what I'm trying to say is consider we are saying that VAB is some voltage,
Hmm.
some non-zero voltage,
Hmm.
and then we say no, sir, that the same VAB means this V in voltage would be reflected on the secondary side as NV in.
Yeah, correct.
So at that time, are we saying that VL will be
Zero.
negligible?
Why I am saying, see, why I am saying it is 0, because L di dt di is not at all changing. So L di dt is 0. So voltage across leakage is 0. So whatever the voltage which are there will be, okay, again, will not be directly here, because the output is also there. So you have to take this one and the reflected impedance from the output side. So it is not just this circuit you have to see. See, you have L leakage, you have to also take down all the things on this side. You got my point? It is like, now it is like a two winding transformer. So in two
Hmm,
winding transformer, what will happen? You have the uh, leakage of one side, then the secondary side leakage or whatever impedance you have, you will reflect it on the primary side. So that's why we have to take it on the primary side.
yes.
I mean, I don't understand exactly what is a doubt.
Sir, the doubt is like, means sometimes, like we are saying that okay, VL leakage would be 0.
Hmm.
So if I'm saying, means if we are saying that in this mode only, if we say that in between T0 and T1, IP is almost constant, and if I'm saying VAB is also 0, then if I am considering leakage, I mean the voltage across leakage is also 0, then VP will be also 0 because VAB is 0. So if VP becomes 0,
No,
then
but that's what I'm saying. No, you have to also take you have to reflect that impedance on this side. There is also other impedance is also there. No,
hmm,
see, other
okay.
impedances is also there.
Okay, okay, sir.
So whatever
And
the current which is there will get reflected over here. That is what you see, the reflected current, IP current. It is
okay,
not like it is short circuited. Secondary is not short circuited. Secondary is now kind of driven by the whatever their primary is not short circuited. It is driven by the voltage which is there from the other side, or you can say kind of having, you can say the EMF which get induced from the during that time, whatever is there on the secondary side.
okay, sir. Yes, sir. Thank you.
You
Understood.
just see the current. In this case you just see the current. If you start seeing the voltage you will get confused. In this case you just see the current. The current is here is nothing but IL, and that IL will reflect in the form of IP, and times
Mm.
IL will be IP.
Okay.
So that
Yes,
has to
sir.
be there. That has to be there. And
Okay, sir.
you see that is the beauty about transformer. It is just the L leakage which will be there, which will take care of the voltage, differences between the terminal and the induced voltage, whatever is there. Is the leakage which will take care of that.
Okay, sir. And sir, when we are saying that VAB, when VAB is negative, then is it like the leakage inductance is responsible to make IP negative or decrease the
No, no,
IP?
see,
And
okay, okay. So now during this time you are saying no, VAB is negative. VAB is
yes.
negative. Now VAB is negative. That means what? The See, finally what happens? Whatever the current you are trying to do it from here, the current was slowly falling down. If you see, the current is not straight line, it is slowly falling down.
Hmm.
Correct? Why? Because
Yeah.
the output inductor current is also falling down because it is freewheeling. There is no
Okay.
active voltage source which is applied across VAB, so it will be freewheeling. Correct? So freewheeling means the inductor current will be falling, the output inductor current will be falling. That inductor current will get reflected on the input side, so that will also be slightly falling. And
Okay,
that
sir.
falling, we have assumed that since the output inductor is very large, so that fall is very small. So you can say kind
Okay.
of neglect, that we have assumed. So now what happens is that, so this current is falling. Now the moment to give the negative voltage across VAB, what will happen? What it will happen is that this current is still be there, which has to be maintained from this point, but
Hmm.
the input side you are applied the negative voltage. So the now the negative voltage, since you are applied the negative voltage, so because of the negative voltage it will try to force the current to have the negative slope, the input the
Okay.
IP slope, and that is when this current will no longer be equal to this current. At this point this current will no longer be equal to
Yes.
this current, and since this current is no longer equal to this current, the what you can say, the current has to, this output current has to find a pathway, and this is not equal to the reflect, because see, previous case what happens was that when it is equal to the reflected current, so they were finding out the pathway through this VAB point. This current was finding a pathway through the VAB point. But now what happens? This
Yes, sir.
current is no longer equal to this current because we have now the active voltage source coming in between. Now because of that, this current has to find some pathway because that's an inductor current. So they will find a pathway through DR1 and DR2. And the moment this DR1 and DR2 turns on, the secondary is short circuited, this voltage is zero. So you can say that there is no presence of the output circuit. You just have this VAB leakage and this short circuit point.
Yes, sir.
See this current, if this current is equal to this current, or you can say this current is equal to the reflected current, this IP is the reflected part of IL, then no issue, that transformer action is still be maintained. If the moment this IP current is ceases to be equal to IL, if this IP current, or you can say it ceases to be equal to reflected part of the IL current, then IL current has to find a pathway, and that will find a pathway through DR1 and DR2, and then the secondary will be short circuited.
Yes, sir.
You got my point?
Yes, sir. Yes.
Yeah. Any further question? One question asked by one of the, let me see that. Sir, can a totem pole PFC stage be utilized as bidirectional front end for designing an onboard charger when combined with a dual active page as the isolated DC-DC stage? See, the answer is, if you use, if the totem pole, if you are using it, not using the diode, if you are realizing it using the active switch, then obviously there is a possibility that you can make it operate in a bidirectional mode also. But you have to use the bidirectional switch. That's it. Yeah, you have to use the bidirectional switch. You can use it. If you cannot able to use it, then you can operate it in a PWM mode. What I'm trying to say is that that half bridge, which is not at all, which switches for the entire half cycle, it is not switching. So what you do is you make it operate as the active bridge. So both are the active bridges, and then you can do the bidirectional functionality. Simplistic way you can do. You make it operate as a H bridge, and then you can operate it. Just like the case what we did it in three-phase system, the same way you can consider this as well.
Yeah, yes, sir, got it.
But ideally speaking, in the totem pole mode also it should work. Bidirectional functionality should work, but we have to see what problems you will face when you are implementing it in hardware.
Yeah, correct.
I have not seen and I have not thought about it. It's a good question. I will look into it. Maybe more
That's one.
concrete answer in the I will give you in the next class, that whether with totem pole you can do the that means you clamping that switch to either VDC and 0, and then you can do the bidirectional functionality. Conceptually, it can be done, because
Yeah, yes, sir.
conceptually if
I
you see,
have gone through some of the
yes,
company's manual. So they are using a totem pole PFC,
yes,
as well as instead of DAB, they were using LLC resonant converter
huh,
for bidirection. I mean C triple LC.
mm-hmm. Yeah, CLLC, yeah.
Ah, yes. And one more doubt is I have is like I have started with simulation of this totem pole converter by using current voltage regulator as well as current regulator, but I can't able to tune the THD less than as per industry standards, less than 5%. Like any source to tune the PI controllers, PI and PR controllers, so that I can maintain the THD.
See, uh, what is the switching frequency? What switching frequency you have kept, if I may ask?
Sir, your voice is too low.
Okay. What what is the switching frequency you have kept?
My switching frequency is 100 kHz.
And what is the power level?
Power level is around 3.3 kilowatts. Like level, it's a level
So,
one.
so you are talking about at the full load condition, or at the uh, your light load condition.
Normally, I did for only resistive load for now. Then I need to replace it. It's a primary stage, right? For checking primary
Uh-huh.
stage,
Uh-huh.
I have did with the
No,
resistive load.
that is
Then
fine,
after,
sir. My question is that have you considered for the full load resistance corresponds to full load case, or resistance corresponds to the light load case?
full load case.
Okay, because totem pole, in totem pole you have this zero crossing problem.
Yes.
Okay, now that zero crossing problem will come into picture you when you will become more prominent when you go to light load condition. And when you go
Okay.
to light load condition, then you can definitely have the problems that your power factor is not matching, your power factor is not going towards 1, and your TSD is very much offset. But if you come near to the, what you can say, near to the full load condition, so TSD wise, I don't think so there will be problem. You may have not taken the inductor value properly, or inductor value, the ripple in the inductor current, how much you have taken, all those things have you taken correctly?
Yeah, I will check once. I will recalculate the inductor
Yeah,
and capacitor,
that
DC
is
mean
one thing.
capacitor
Yes,
value.
DC link capacitor value is okay, but the inductor is important. Then second thing is that you can also do one simple thing. You can compensate that zero crossing point.
Okay.
How you can compensate that zero crossing point? I mean, there are techniques where you can softly, what you can say, softly do the transition of the totem pole bridge, or the bridge, or the half bridge which is either clamped to VDC or 0, that means the slow switching bridge. You can see there you will find some of the application notes from TI. You will
Yeah,
able.
same. I gone through the Infineon Technologies
Hmm.
application notes.
Yeah, so there you can compensate that zero crossing. It will not go to zero, but you can reduce it to very minimal. And also I suggest from my personal experience, you try to use either SiC or gallium nitride devices,
Okay.
because the IGBTs will have good amount of because since the IGBTs are basically rated for higher voltages, so what happens is that their output capacitances are enormously higher, output capacitance of the devices. So you will not get the sharp transition of the devices.
Okay. Got it.
However,
Got it.
however, if you use the SiC or gallium nitride, you will see that that zero crossing problem will be less as compared to the case you see in the IGBT case, or
Huh.
silicon MOSFET case.
Yeah, silicon carbide MOSFETs.
What I'm trying to say, if you're using, if you can also change that IGBT or silicon MOSFETs to silicon carbide MOSFET or gallium nitride MOSFET.
Yeah. Yes, I will try. Sir, like once.
And I also suggest don't go by the numbers which you get it in the simulation. You put it in the hardware and see.
Okay.
Why? Because in simulation, if you, let's say you are doing a MATLAB modeling, you are doing the behavior modeling. You
Yeah.
are not considering any circuit parasitics. But that zero crossing is primarily because of the output capacitance of the devices and the what you can say, primarily because of the output capacitance of the devices, because it will take some time for the devices to change its state. So I will suggest you either you do the simulation in Spice simulator, or you can say
Yeah. Spice. LT Spice.
LT Spice or P Spice. But again, there how, I mean, you have to see how you put the closed loop control and all, or you do it in a hardware and then see whether you are getting the TSG properly or not.
Okay, sir.
Yeah. But when I made the hardware, I did not find any problem from the TSG perspective.
Yeah, I will check the zero crossing frequency as well as
Yeah.
the load conditions
Yeah,
and
and
inductive calculations.
I did it for 1 kilowatt. So and again, a 1 kilowatt is pretty much. I mean, with 3.3 kilowatt, you have good amount of fundamental component of current.
Ah, yes. It's like as per AV, it is like level one
Yeah, yeah, yeah.
charging. It
I
comes under
think
level two.
it will peak value will come somewhere around, if I'm not wrong, 20 ampere peak value of current.
Yeah,
So
yes. Current is around 20 amperes.
peak current.
Yeah, yes.
RMS is 15 or 14. So
Yes.
yeah, so it is good amount of current, because generally you keep the ripple within the one. I mean, 10%. You can say 1 volt peak to peak, or 1 ampere peak to peak. So 1 ampere peak to peak means it is a slightly. I mean, it is a very small ripple component is there.
Huh.
What is the ripple current? What you got?
I kept a ripple voltage. Ripple current I have I not kept. 1 minute, sir.
No, L value you will only obtain using the ripple current.
Yeah, 10% or 20% I took. Exactly, I
20,
can't remember
no,
it.
if you put 20% is too large.
Huh.
You put it either 5 or 10, your inductor value will go up, but you put it 5 or 10. There's no other way
Okay.
you can do it.
Okay, I will change that. I will see the in simulation once.
Yeah.
Okay, sir. Thanks, sir.
Then any further questions you have?
Sir,
Hmm.
in lecture 39, while we are seeing the effect of DI, the, what is T45 old? I didn't understood it properly in that case.
T45 old.
Yes, sir. In lecture 39, slide 7.
Okay. See, uh, previously your value was from this point to this point, T45 value, and now
Yes.
your T45 value will be from this point to this point.
Okay.
Okay, that means from this point to this point.
Yes.
That is what I have written. If I take this as a mid, sorry, let me take down. I think I have to enable it. Huh. See, if I if I take my this point to if I take this point to this point is my T45 old, and if I take this point to this point is my T45 new.
Yes, sir.
T45 new. Okay. Now, if you see in this one, delta NIL plus and this small IL which got. So what happens is that when this thing is there, see, when it was not there, it has to be at this point. It has to be
Yes.
at this point. And when it is there, it has reached to this particular point. I mean, from this point to this point, it has gone from this point to this point. So what I have taken is that in this one, it is L leakage NIL. It has gone up NIL tilde by V in, because we have taken the things from.
Sir.
Let me think a bit. Ah, okay. So this point is what? This point I can say this is N IL on one side, and this point I can say from this point I can say this is again NIL tilde. This point, from this particular point, if I see the previous one, I mean at this point it is reached beforehand itself, NIL,
Oh,
and
yes, sir.
after that, after point this, it will reach, because of this slope, it will reach NIL bottom, I mean below, because of
Yes.
this particular thing. So that is why it is 2 times NIL which has come into picture. In a way, what I have written down is that in the previous case, till this point to this point, it was, if I take this as a nominal case, I have taken NIL minus small changes, and on this side I have taken plus small changes which I have got
Oh,
from this,
yes, sir.
on this point. From this point I have taken. That is what I have written.
Okay, okay, sir.
From this point to this point. Basically, I am talking about from this point to this point, I am seeing whatever is there, whatever the delta t. So if I take this point, it is, if I take this value from this point to this point, it is still what you can say, if I take this as NIL minus, uh, from this point it is minus NIL tilde, and from this point, sorry, from this point till this point, it is, if you see, it is 2 times, NIL minus plus NIL tilde, and that is when you will get 2 NIL delta.
Yeah. And such a arrow you just draw, that is 245 new, means the arrow you just draw,
Yes.
that is
Yes.
245 new.
Yeah, 4 5 new, T45 new, yes. And this one was T45 old. That is why when you wait, let me see.
Okay, sir.
Let me think. Let me think. Ah, I'm talking about this is the T45 new, and this is my T45 old. This one. So new minus old will be this part. New minus old will be this part. I think I'm talking about this part, T45 new. From this point to this point, I'm talking about. Basically, this T45 I should have written this tilde, something like this. Tilde I have to write, not
Mhm.
this one. If I so this is the part I'm talking about from this point to this point, and this is just from this point to this point to this point. So when you take the inverse, I mean difference of that, you will get this value. Only this point,
Yes.
that point you will get.
Yes. Yes, sir. Yeah. Thank you, sir. Understood. Means like delta T is basically the change. We can say that the
Yes,
change in the current is to twice of
twice
NIL.
of Ni, because from this point, if you take the nominal value, it goes in this side, it goes on the other side.
Yes.
Any
Thank you, sir.
further questions? Okay, if no further question, let me uh, discuss things related to the next assignment. See, in next assignment, in total, if you see, there are, first question, it is straight from the, you can just look into the concepts and solve it. Second problem, still it is given that the thing, you can just use this formula. You can directly use this formula P average, which is there, nothing but equal to 1 minus delta star times V naught mean by 2 and L FSW. And we also know that our P average maximum value is nothing but our V naught mean by 8 and L FSW. So you can directly, the questions is given, already what is P average maximum value, put it on the required thing. And then we have also given one condition where our phase shift is kept at 90%, 90 degree. So accordingly, you can there you may get two values because you have quadratic expression. From there, you can calculate one correct value which is satisfying this particular criteria. So that is the kind of thing. Then in question 4, we have already discussed for question 4, we wanted to have the minimum total loss, minimum P total. For that, we have done simple P total, differentiation of P total with respect to delta B is nothing but we did it equal to 0, and that we can say dPCU total divided by d delta B plus d P4 divided by d delta B equal to 0, and then you rearrange this one, what you will get is d delta B is equals to minus P4 by d delta B. Now this you can use that in this one, and already PCU total value is given, P core value is given, just you do that particular expression, using this particular expression you can easily solve this particular problem. I think you can easily get the relationship. Or you can easily get the optimum value of delta B. Straightforward question you can say, because you will get in terms of delta B, you rearrange them and you can get the delta B accordingly. Then comes your question number 5. Again, you have to by seeing the inductor current, you have to see what the relationship between V in and V naught by N, where we know what is our N. It is nothing but Ns by Np. Then comes the question number 6, where the question is, let's say if there is a phase shift between the one of the half bridges, so how the inductor current, or how the inductor, how the voltages will look like for the from that full bridge. We have also discussed this in one of the, I think in the first lecture or in the second lecture, briefly I have discussed that. So you can just follow that and choose the correct option. Then again in question number 7, question number 8, it is directly straightforward. Using the formulas you can put it and you can obtain this particular, these two are the only two problems which will be only two expressions which will be, you will be needing it while solving the expression, because we have considered it is a SPS modulation, because with double phase shift and as well as sorry, double phase shift and triple phase shift, or dual phase shift or triple phase shift, you have a lot of big complicated expressions which you can solve it following the method what we discussed in the course. Yes, any further questions you have? If no, then we can stop for now.